here to talk to you a little bit about the SST chip, which is the Single Chip Series 10. It was the first cost reduction done on the Voyager family. So this is what I'm going to try to cover with you today. Talk a little bit about the Voyager context as how it fit in HP, what the SST project goals were, the HP organization context around that product development, little history on the Corvallis site, how this relates to Return of the Jedi, and then a little bit more in detail about the design team, design description, how we did the design, and how we verified it, and then some project surprises. If we have time, I have some epilogue work, some pictures of the Voyager cost reductions that have happened since SST. Okay, so Voyager was a big deal to the Corvallis site. This is actually the cover page of an employee newsletter in Corvallis, and I didn't retouch this photograph. So the star on the Voyager calculator was there on the issue, and so you've got a picture of Dick Moore and Packard, and they say in that picture that the calculator is the star of the show, not Packard. Okay. One of the inside pages of the newsletter is on the right-hand side, and one of the things they say at the end of it is that this was published in the local newspapers, technical journals, and the local television stations. So this was actually a big deal to the Corvallis site. Now, inside this newsletter, on the cover page, okay, this was the notice from the general manager of the components operation, and in that he says that Voyager required the largest chip ever done in the Corvallis fab at the time, and even though it is too big for large-scale production. That's a hint. Okay, the design was too big to actually make a whole lot of money with it to begin with. Okay, even though it was too big for production, we built tens of thousands of these circuits and made introduction of the calculators possible months earlier. Our new higher density process will help us be more cost effective. And so he's laying out, this is the newsletter that went out to all the employees on the site saying, okay, you guys, we have to build a new, cheaper version of this. So the SST project goals. Voyager was doing well. Okay, it was very popular when it was released. Voyager was high volume for HP. So there was a big drive to cost reduce the Voyager product line, to reduce the number of ICs from 2 to 1 for the HP 10, the 11, the 12, and the 16, and to reduce the number of ICs in the 15 from 3 to 2, and to use a 2-layer PC board. Okay, multi-layer PC board was too expensive for the product at the time. SST at the time was viewed as a short-term cost reduction because the Voyager was going to be replaced by the Pioneer series in 1 to 2 years, and so it was the 12C would never be sold after 1982. Okay. So this is a history chart. This is actually somewhat redacted. This is from an internal celebration newsletter, and it talks about a little bit about the history of the fab that made the Voyager chips. First of all, why Corvallis? Do any of you know why the calculators were being done in Corvallis? Okay. Turns out that HP had a strategy for risk reduction to geographically diversify its operations across the U.S. Having everything in San Francisco where an earthquake could take out the whole company wasn't viewed as a good idea. Okay, so they said, we're going to geographically disperse. Now, where are we going to put? And they decided that they wanted to be at cities that had strong technical universities, engineering schools. Fort Collins and Corvallis. Well, why Corvallis? Well, it turns out John Young, who was the CEO of HP was an Oregon State grad. Okay, so it was and it turns out that Corvallis was a very positive place for them to put an IC fab. For IC fabs, you need water and you need electricity. We had both in Corvallis. So this is the history of Corvallis. So the plan was always to have a CMOS fab in Corvallis to support the calculator operations. And originally, the fab reported into the calculator division, but eventually it was split off as its own organization, and that'll be important pretty soon. You notice that wished I had a pointer. In 1980, we had CVD, PCD, and CCO. CVD is the calculator division, PCD is the portable computer division, and CCO is the Corvallis components operation. That's the group that did the chips. Okay, so this is an organization from my vantage point. These are all of my HP badges. Okay, we called them the chewing gum badges because the badges were about the size of a chewing gum pack. HP went the way a lot of other companies did eventually of having big picture badges, but for a long time these were all the badges that you needed to get in. So I joined HP in 1980. I joined in CVD. I worked on the HP75, and then I worked on the HP75 pod. Okay, and I went into production with the HP75 pod. When I was out there, I got offered a project manager position. When I went to production, okay, I was offered a project manager position in the Northwest Integrated Circuits Division, which was the IC group. So this is not the calculator group. I was moving over into the components group as an IC project manager. So my first project was SST as a project manager. Okay, so why does SST relate to, how does it relate to Return of the Jedi? At the beginning of Return of the Jedi, this is actually from a project management website, believe it or not. You have Darth Vader landing in this partially complete Death Star 2, and Darth Vader lands and he's talking to the commander of the station that's in charge of getting the station in shape. And this is the dialogue from that initial conversation. The project manager says, "Lord Vader, it's an unexpected pleasure. We are honored by your presence." And Vader says, "You may dispense with the pleasantries, Commander. I'm here to put you back on schedule." The manager says, "I assure you, Lord Vader, my men are working as hard as they can." And the station manager says, Vader says, "Well, perhaps I can find new ways to motivate them." Okay, I tell you, the station will be operational as planned. And Vader says, "Well, the Emperor does not share your optimistic appraisal of the situation." Project manager says, "But he asked the impossible. I need more people." Vader says, "Well, perhaps you could tell him yourself when he arrives." Vader says, "Well, the Emperor's coming here." "That's correct, Commander, and he is most displeased with your apparent lack of progress." Okay, "We shall redouble our efforts." "Well, I hope so, Commander, for your sake. The Emperor is not as forgiving as I am." So I felt during the SST project, both as, like Lord Vader, I was joining a project that was behind schedule. And I also felt like the station commander in the management reports where I, as project manager, had to report in our progress on the design. We did get more people. The Corvallis team, I could not have asked for better. We brought in the HP41 CPU designer. We had the Voyager IC designer, so the first generation chip designers brought in. The Singapore, we also brought in a team of engineers on long-term assignment from Singapore. And it's an awesome group of BSEEs, MSEEs that went on to become the HP Agilent Penang site R&D manager, the HP Singapore site R&D manager, engineers and directors and vice presidents at HP and other sites. So this was a stellar group of folks. And I've listed the names on the right, and I profusely apologize if we missed a name or two. I went out and talked to 3 of the team members, trying to remember all the names. We did our best to get it. This group worked long, hard hours. We had a blast, and we formed friendships that lasted for decades. SST design. The Voyager schematic it was hand-drawn on one E-size blue line sheet, and the tool that we used was that logic template. Okay, that was our schematic capture tool. All previous designs were full custom. And by full custom, I mean full custom CMOS. So we had and inverts as all one gate with PMOS. We had transmission gate logic. We inherited some of the original design practices from HP Labs when they had done some of the work on the 41 series. So all the chips were full custom, and there was, at the time, a lot of skepticism that it was even possible to do a standard cell place and routed design. We were told it couldn't be done, let alone as a cost reduction of a handcrafted custom design. So we partitioned the SST design into custom blocks and standard cells, and we used custom cells for density: RAMs, ROMs, shift registers, phase PLAs, and analog. And we entered the schematic for the standard cells and did place and route. What you see there on the side was one of the design team looking at a Calma artwork plot up on the wall, and that's part of the way we did our continuity check, and that is our schematic versus layout check. Okay. So this is the SST chip. So this is the single super chip for the...
Chuck, can I just take you back on that previous picture?
Yeah.
So how many sheets? Is it the whole wall? Is the whole diagram? So from the front of the image to where Ray is standing, is that the whole chip?
Yes.
Is that 2 or 3 copies?
No.
People looking at that?
There are a couple of sections which are duplicate, but they're blow-ups of, especially the analog, where we actually did more precise checking of widths and spaces for coupling and that kind of stuff.
Well.
SST. So this is this is chip picture. This was, again, the goal is a single super chip for 10, 11, 12, and 16. This is HP's first standard cell CMOS calculator chip. This is a little of the detail in it. You can see the analog on the left, the display shift register, and then the RAM and the ROM, the phase lock loop. And I noted flip-flops. Those we also called those route obstructions. Our CMOS process was designed to be very low leakage, but it was also very low cost. So to put things in perspective for people that are familiar with CMOS processes, this was a 1-layer poly, 1-layer metal process. Okay, so the flip-flops used all of the route channels to connect up internally, so you weren't allowed to route over them. So they were huge. The other thing at the top in the middle is the coupling cap. We tried to get rid of the coupling cap, the keep alive cap in the calculator, so when you take your batteries out you don't lose it. We tried to put that on chip, but we couldn't get a big enough capacitance on chip, so we just use that for noise reduction. There's more routing around the top row of the pads and along the side on the left, because we did the layout of the PC board and we rerouted the pads and shuffled the pads to guarantee that it was going to be on a 2-layer PC board. So it was cheaper to do routing on the chip than it was to have a 3-layer PC board. The pads also have a lot of extra logic around it for ESD and latch up. So on this CMOS chip, we put a lot of extra structures, diodes, and whatnot in there to prevent ESD. At the bottom middle, I'm almost reluctant to mention this to this group. We were also the first calculator chip that put the MassWorks and copyright protections on the die. That's why people that were doing emulators and whatnot had to go and get permission from HP, if HP would give it to them, to use the ROM code in this, is because it was copyrighted.
Before you continue, can you give us some numbers, some statistics about the size of this thing?
I think it's in my article. I can't recall offhand.
Okay.
Verification. During design, we use Voyager functional test vectors to logic simulate the whole chip. This was running in the very low parts per million defect rate in production. And so we had a high confidence that those functional test vectors, this was before scan, so you didn't have scan, so functional test vectors were good enough to verify the part. So we used those to verify the design. We used HP Spice and not the Spice that was at the dinner table last night. This was a version of Berkeley Spice that was custom done by HP with special models that was very accurate. Dick Dow was the person that led that effort there. And we spiced the simulated custom cells. We also spiced all the critical timing paths and the analog. DRC and LVS ran on an Amdahl in Loveland, Colorado. It's the same Amdahl that HP ran its books on. It took 2 days to run a full DRC on the part. During manufacturing, we used Schlumberger Sentry 7s and Sentinels for full pattern, basically functional pattern testing and electrical spec testing. We did multi-pattern RAM retention testing, and we did ROM verification. For prototyping, so that, by the way, over there is the picture next to the Spices is the Amdahl. The Sentry is below it. For prototyping, we did large prototype builds, and we basically handed out the calculators to just about anybody on site that wanted to sign up to do testing with the calculators. We also had technicians verify every manual example in all of the manuals. So the 10 manual, the 11, the 15, the 16, they went through every example by hand with one of the calculators. And that's why you see the calculators at the bottom in the manual. Okay. So this is a Voyager system. So this is before SST. This is what a Voyager system looks like. And by the way, I've got one of these in a clear backup here for somebody to look at the break. So the Voyager system had the 2 ICs at the top. You'll notice that it's on a brown PC board. That's a polyimide PC board. That's an expensive PC board. Polyimide was used at the time because it had the same coefficient of expansion about as silicon, and so for reliability. But now you see at the right-hand side of the display, there's a PC board to PC board connect down to the PC. That's that brown thing on the side. That connects up to the keyboard PC board below, and then you see that the keep alive cap, the big keep alive cap, and a big resistor and a little capacitor. The resistor and capacitor are for the on-chip oscillator that required those two. So this, if you compare this to some of the stuff that you can see in data file and everywhere else, this is actually substantially simpler than a lot of, if you open up a 67 or 65 or whatnot, this is substantially similar. So everybody knew that this was going to be high volume, and they did their best to cost reduce the part. Okay, so that's a Voyager system. This is an SST system. Oh, wait, actually this is the same one. It's only in the clear back. I forgot to mention there's an ESD spring, and this is actually still in the calculators today. That's an ESD spring that goes from the overlay of the keyboard to the overlay on the back, which were both metal. And what that is that's our best attempt at a Faraday cage to conduct ESD and stuff away from the fragile electronics inside. Okay, this is an SST Voyager system. One PC board. one IC, surface mount, the big keep alive capacitor, 2 surface mount parts, a resistor and a capacitor. I still got the ESD spring. As you can tell, this is substantially cleaner, substantially more production worthy.
May I ask a question? What year was that introduced? This new
80 in the 80-83 time frame.
Okay.
Project surprises. Okay, the big one, and you guys already laughed at this earlier, is that the HP12 was not obsoleted by Pioneer and is still going strong. The SST project has had a very positive ROI. The HP12 outlasted its fab process. It's outlasted a couple of fab processes. The fabs have obsoleted their process. The SST was not the last Voyager re-implementation like we were told. Okay. Next surprise is how much less robust the semi-custom autoplace and routed designs were than their original custom designs. The original custom designs were handcrafted and they were tight tolerance. Okay, so what we found is that when all the appropriate parasitics were considered, HP Spice was reliably spot on accurate. But we weren't able to run with the computers we had at the time full chip Spice. So we had to make simplifying assumptions, and those simplifying assumptions caught us every time. It turns out that when we had a problem, and we had problems in the design, when we had problems, we were able to go back in HP Spice and find it. Okay, one example that we found late in development was the on period bug that due to a timing race. You remember I said that one of the things that this passed, by the way, this part passed all of the functional vectors, but one of the things that wasn't checked was the timing on the on period. So do you guys know what the on period does supposed to do in a 12? It's supposed to convert a period to a comma and vice versa. Well, it turns out on one of the versions of the part, when you hit on period, you get the display that looked at the bottom. All the commas came on. And there was a race due to a race in the part. Well, that was found because of the extra rigorous testing where we had everybody running all of the examples in the manual. Somebody was doing the 12C manual and came across, well, you have to test this on period. He did that and he found that. That's the way we found it. Better to find it that way than when it went out to production. We made a lot of 12Cs with this. Okay, this is another marginality that we found. This is a picture of a marginal SST calculator, but it's working. Why? Anybody have any idea? That little star, for the people familiar with Voyager series, is a low battery indicator.
I've never seen one of those. I've never seen that indicator come on.
Yeah.
Well, it turns out that you're not alone. HP, as it was selling its Voyager line, okay, the service department, when they got a Voyager calculator in for service, the first thing they did is they turned over the calculators and put new batteries in. And about half the time, the calculator worked. People didn't realize that the calculators needed batteries. They ran so long on their battery. That contrast that with your cell phone, which you hope you can get a good day out of.
Yeah.
Okay, so yes, the low battery indicator is a clue, and this is the label that I hid in the last drawing that says that it needs to run at 2.7 volts. So now we said how it's working. So how do you think we got this working? Well, flip it over. This is a picture of the back of this calculator. It's a 15. So a 15 has 2 chips. It has the SST chip and it has an extra ROM chip because there wasn't enough ROM on. We built the ROM, sized it just enough to do 10, 11, 12, and 16. And the 15 had twice as much ROM. And so you didn't want to put that extra ROM and make the base chip more expensive. So it had a second ROM chip. Well, let me zoom in on the battery compartment. Okay, the battery compartment, that's 2 batteries and a nylon washer and a diode in between. Okay, so that's 1.5 plus 1.5 minus a diode drop gets you to the voltage that this calculator works at. Why did we do that? We did that so that we had a mini production line building this setup so that we could hand the calculators out so that we could continue to do testing and not be slowed down by the marginality of the part. Okay. So, how am I doing on time? Okay. So I've given you a Voyager context. I've talked about the project goals, the HP organizational context, the IC and the design team, the project surprises. So go on a little bit. This is a Voyager family, and the black and white pictures are actually from data files off of Eric's drive. Let me start by answering one of the questions that was actually in the data file. The picture, this one, there was a question about why does it have an Agilent label on it? Well, turns out that just as going on now with the HP split, when Agilent split from HP in 2000, they were only allowed to use the HP name on products for a very short period of time. And so Agilent was required, and the fabs went with Agilent. The product stayed with HP, but the fabs went to Agilent. And so the part name the part package name has to change to Agilent. Had to change pretty quickly to Agilent. Now, a fun fact is if you decap that part, so if you took the package off and looked at the die, you'll see that it's an HP die. It says HP on the die. And that's because the business guys, when they were talking about how long you could use the name and whatnot, they realized that having to change photomask tooling was very expensive. So they didn't require the photomask name to change, but they did require the outside packaging labeling to change. So that's why, to answer the data file question from a long time ago, that's why it's Agilent instead of HP. Now, to me, what was surprising is in the bottom 2 corners, this, by the way, is not all of the versions of Voyager that are out there. There's a couple more that I don't have, and it used to be, and from the data file article, I remember that it used to be that at these meetings they would actually take apart Voyagers to look at the different versions. Now, I'm having trouble reading this because the fonts got squished up by Microsoft PowerPoint. But there's a quote under there that's, why do this? So far as the user is concerned, all 12 Cs work the same way and give the same results. Yet to some HP fans and hardware hackers, this is not the whole story. We want to know how it works and how it changes. That's a quote from our first speaker from back in the data files, and I thought it was particularly apt in terms of what goes on with this. By the way, I have some of these printed out as a 8.5 by 11 mini poster. Okay. Now, what surprised me, by the way, was in the bottom corner, there's an HP, the latest HP Voyager and the Swiss Micros Voyager. Okay, so this is the single chip. Okay, this is the latest HP Voyager. Blow up of the PC board size. Just to put this in perspective, it's got an Atmel 128K byte flash, 6K byte SRAM, 7-segment driver. It has the calculator has 33 surface mount components. Okay, it has its own power supply chip, power supply regulator over on the left-hand side. It's a multi-layer PC board. Okay, so this is quite a complex beast compared to what we used to be. But the reason is this was because they're using off-the-shelf parts to build it. Now, the DM15 is similarly complex. So that's the Voyager family. Now, an epilogue for HP semiconductors. The B3 fab that was built in Corvallis to do calculator design was very low leakage. We talked about how the battery life was done purposely to have low battery life. It also turns out that in 1976 to 78, it was one of the few CMOS fabs in the world. At the time, Japan was still in MOS. RCA was doing CMOS. Okay, not very many other places. So this fab was built to do pocket calculators. Turns out it worked out for other things, though. B2, a higher volume fab, lower density, CMOS, more advanced processes, was built in Corvallis. We actually offered foundry services, supercomputers, PC graphics chips, error correction. We're in satellites for ZIF error corrections, that kind of stuff. HP transitioned from internal CMOS ICs to being a foundry service customer. It transitions at B2 fab, the Corvallis fab that did calculator chips, into inkjet head manufacture. And it transferred from doing internal CAD design to using industry CAD. The HP site, in 1980, we had the three green buildings, building 3, 4, and 5. At the time, building 5 was initially empty, so when I joined HP, we actually played Frisbee in the upper building. It was all open space. The building 4 had a cafeteria, offices. It had its own plastic molding, so the double injection molded keys and whatnot were done at Corvallis. So all the Voyager calculators were made entirely in Corvallis. And at the time, the GM bragged that the person that did the plastic molding design was paid more than he was, because it was so critical to get the yield out of the plastic. Okay. Later, a cafeteria was added in the B2 Bigfoot Fab number 2. Service was in the small building. This is somewhat after that. What the site is today, HP's still there. It's not occupying all the buildings. It's basically a business park. And they even demolished one of the buildings because it wasn't in use. And you can see some of the things that there's actually nuclear reactor development going on the Corvallis site. NuScale, interesting. You should look it up if you haven't heard about it. Polycom had an office there. I think they're still doing R&D there. So at the end of the presentation, and this is on the drive, I did several versions of the family. This one is the one with just HP. This one has Swiss Micros, and this has all of them, and it's printed in landscape for that. This is the one I've got pictures of. Okay, so that's it. Any questions?
Well.